since I actually mentioned that in class too, I think. Right? So we have an inclined plane. And then we have the spring, right? Isn't that it? No?
Yes.
Yes?
Mm-hmm.
Okay.
Sorry, I didn't read that one
Okay. There's a spring in the cart, and
yet. K equals 0.8 newtons per centimeter.
0.8 newtons per centimeter. Okay. And it's asking how high up the inclined plane can it go? Now this is a pretty trivial problem, but it's going to say it's going to get pushed, and at the highest point, let's say right here, the highest point. Okay, this is highest point means what? Means that this guy's only got what kind of energy?
Potential.
Potential energy, right? At its highest point, it means the speed going up stopped.
Mm-hmm.
So we'll call this height h for now, right? And we know the angle of the cart. Yeah. We don't really
8
need
degrees.
it. We don't really need it, but
Oh,
I mean, we'd need it if we were doing the friction. If I included friction in the test,
yes,
What
that's
we're-
neglected.
but it's neglect friction. Okay, so we know the potential energy here. Do we know the potential energy here?
It's a 0.
The potential energy here is equal to the energy stored in the spring, right?
Mhm.
Which is equivalent to the work it takes to compress the spring, right? Which is going to be the 1/2 k delta x squared. So the spring is compressed initially, 0.3, what was
3 centimeters.
3 centimeters?
Mm-hmm.
3 centimeters? Okay.
At
Seems
time
small.
0. And then it's,
What?
so never mind. I was just reading the rest of the sentence.
Okay, so the potential energy here has to equal the potential. It's the trick of the whole problem, right? So that means the potential energy at the top, right, equals the potential energy at the bottom. Okay, at the top is going to be the mgh. At the bottom, it's going to be the 1/2 k delta x squared. And it's actually asking for the height. Right? No, it's actually asking for this distance d up the track, right? So that distance d is going to be what? Remember, h over d gives me the sine, right? H over d gives me the sine of the angle, right? So that means d is going to be h over the sine of that angle. So I can, or actually I can just solve for h. So I'm sorry, let me do it like that. Let me just solve for h. Because I'm going to plug it in here anyways. So h equals d sine of the angle. So I can plug it in right here. So I have mg d sine of the angle equals 1/2 k delta x squared. I'm going to divide everything except for the d. I'm looking for d. How far up? It's going to be k delta x squared over 2 mg sine of theta. So I've just divided all this stuff over, right? And then we can plug the number in. So keep in mind this is 0.8 newtons per centimeter. We want this in meters, right? So doing it in meters, how many centimeters in a meter? How many meters in a centimeter? So it's 100, right?
Yep.
So we're going to move this 2 decimal places over, right? So it's 0.8 basically divided by 100. No, sorry, multiplied by 100. Newtons per meter. Okay. And then delta x was, how much was it? 3 centimeters, you said?
Yes.
So it's going to be times 0.03 meters squared, right? Divided by 2 mass in kilograms, if we have the mass.
500 grams.
0.5 kilograms, right? So it's times 0.5 kilograms times 9.8 times the sine of 8 degrees, or?
Yes.
Okay. So that distance, what is it? I don't know, 51 centimeters? No. 53 centimeters? No. those of you guys start having these kind of things to do in a calculator, it's always better to do this number first on the bottom, get the answer, and then hit the x to the minus 1 button, which drops it on the bottom, and then just multiply by this stuff on top. So you never have to work on putting brackets and divide and all that stuff, whereas where most people make mistakes. You'll find that your errors go away really quickly when you do it that way. And if you don't know how to do it that way, let me know and I'll show you.
They're at 0.0527.
0.05278. 3 meters, right? 5.3 centimeters.
Mm-hmm.
Yes. Is it, I feel like so this is 880. This is 0.03. It was 3 centimeters.
Yes.
Okay. Wait. Yeah, 3 centimeters, 0.03. That's right. Okay.
Yeah, I just redid it.
Yeah,
Unless
but
I plug
this is a really, sine of 8 is a really small number, so I would have expected, this is like 10, but this is a really small number. So, I would have expected that would have,
Yeah, it's a 1.36.
1. Sine of 8 is like 0.00 something, right?
0.139.
Yeah.
0.139, okay. So then that's 10 times on top, okay, gotcha. Okay, so that, I mean, this number looks right, I just wasn't sure of the decimal place. Okay, so that's number 4, that's not too bad, right? What did we do? Remember, like we did sum of forces, now we're just doing sum of energy, same process as before. You draw it, in this case, instead of sum of forces, you're doing sum of energies and solving for the unknown, instead of solving for acceleration. Right? So you get to skip the acceleration part. Okay, and then number 1, I guess, was the